Good morning, colleagues. I hope you're all safe and well in these troubled times. Today, a great privilege in introducing to you Dr. Suresh Kumar. I'm going to call him Suresh because he's a good mate of mine for the past 10, 15, 20 years. We work together collaboratively on many tall building projects where I am the structural engineer and Suresh is the wind engineer, two very important disciplines for tall building design. Today, Suresh is going to talk about wind speeds in India. As most structural engineers know, wind speed has a huge influence on the structural design of tall buildings. In India, with many tall buildings going up, wind speed have a huge influence on the cost of the tall buildings. I'm hoping today that Suresh is going to come up with lower wind speeds for India, because we find that in India, the wind speeds that are adopted are relatively quite high compared with corresponding places in the world. Suresh is a leading wind engineer and he works for a leading consulting firm. He's a director of it, RWDI, originally based from Canada. And what Suresh has achieved is amazing, because not only is a great wind engineer, but he has opened up a wind tunnel facility in India. Well, people might not realize that there's only 2 or 3 countries in the world that have actually wind tunnel testing facilities. So without further ado, I'd like to introduce Suresh and presenting on reduced wind speeds for India. Suresh, welcome, and we look forward to hearing from you.
Good morning, everyone. Thank you, Anil, for the kind words. We have been working together for a long time, and we'll continue to do so for several years further. And before I start to discuss about the subject matter, I think I have to thank C2BUH team. It's a great team. I mean, I'm not going to name everybody, but it's a great team working together and bringing this presentation possible. So the topic of the presentation is written as revisiting wind speed of India, and Anil has already brought up the issue of whether to reduce the wind speed of India. Let us go through the presentation and see where it is possible to reduce the wind speed of India. So just to give you an outline where I am going with this presentation, when we are analyzing our own wind speed map, it is also wise to look at what others are doing. So I'll be looking at major international codes and see what they are doing with their wind speed. And then parallelly, we will also look into Indian code and discuss about the wind speed. And then I move on to cyclonic wind speeds. Primarily, this presentation is for cyclonic wind speeds of the coastline of India. The reasons are well known, because as you know, recently number of cyclones are passing our coastal lines, and there is always a worry whether the speed is going to be increasing in comparison to the code speed. So that is boiling down to the discussions where I'll be comparing again back to the rest of the regions, in fact the whole world in terms of the wind speed, and then try to position ourselves where do we stand in terms of the wind speed. Then a few conclusions, and that is when we'll go into the reduced wind speed aspect. These cyclones are already known to you because you are following the media and the papers. Cyclone Amphan and Cyclone Nisarga recently passed the Indian coast on either side, one on the Bay of Bengal and one on the Arabian Sea. The Arabian Sea one is a surprise, because typically you don't see cyclones passing, crossing from Arabian Sea side. There are reasons for that, which we'll discuss later. And another thing probably I wanted to point out is when the cyclone is inside the middle of the ocean, typically it is very strong. And when it is getting closer to the landfall and landmass, it will reduce the speed. That is very typical of any cyclones, typhoons, hurricanes around the world, which we'll discuss later. This is the crux of the issue that we are talking about. So we have to look into IS 875 Part 3 wind speed map. There are 6 colors, 6 speeds. So basically 6 zones. So you can see coastal zones itself is having multiple zones. And then most recently, there's another code came up with another wind speed map, which is in NBC, National Building Code of India, where you can see there are subtle changes between the 2015 code and the 2016 version. The Delhi region is getting some changes, as well as many other locations if you go through very closely. So there is already a confusion which is to be followed. When we were doing projects in Delhi, some people are saying, okay, use 47 meter per second. And another set of team is asking for 50 meter per second. So this issue has to be resolved very quickly, because otherwise you will see different wind speed being used for the same location. And another few things I'm noting here is abrupt changes in speeds. You should take a look at the northern India, for instance, the Kashmir region. You can see the very topmost, you have 55, then jumping to 39 meter per second to 47 meter per second. So this is a very abrupt jump here. And I know that we have done some projects in that 39 meter per second zone, which is all full of mountains. Then we found out that that is not 39 anymore, it is 49 meter per second for a bridge project, which we have done some time back. So basically, I want to caution you that whenever you use this map, you have to also look at the local terrains, because whether you have mountainous terrain, if it is mountainous, you may have to use topographical factors, or sometimes you have to even get into topographical wind tunnel simulations, because otherwise none of these speeds makes any sense. Regardless of all of these issues that we are talking about, today's talk is primarily going into the cyclonic factor and cyclonic speeds. Why we are too much interested on that is we are further trying to increase the speed, which is in the map, because the map is saying ultimate speed is 55. But according to the code, we came up with cyclonic factor, which will elevate the speed further, which we'll be discussing soon.
Suresh, just a quick question there.
Go ahead.
For us humble engineers, which code should we be using?
That's an interesting question, but I would tempted to go with IS 875 Part 3 2015, because it is supposed to be the wind code. Because whenever you wanted to do calculations, you require other factors and etc. So you cannot go back to any other code to pick the factors. So once you are in this code, you have the speed, you have the factors, you can calculate everything. But the National Building Code of India, Bureau of Indian Standards should immediately update the map inside the IS 875 if this is the path that we are trying to follow, actually, because otherwise that will confuse the public, because we have been using multiple speeds for Delhi right now. All right.
Thank you.
Now getting into the importance of wind climate, because you have multiple links in this chain. This is a famous wind loading chain from Professor L.N.G. Davenport from Canada. In order to find the wind load, you need to have these links. And all of these links are important, but wind climate is the super important link in this one, because the coefficient of variation in this link is too high for the wind speed, so which is about 10%. And how this is going to impact our structures, local pressures are increased by V square. That means if you err on 10% of wind speed, your cladding loads are going to be 20% higher. But in structural load, the complications are more. It is not just V square, it could be even V cube. That means when your speed is increased by 10%, your overall increase in structural load could be anywhere from 20% to 30%. So which is very, very critical for the design is concerned. So that is the reason why wind speed is very important. But the interesting thing is the wind tunnels doesn't have anything to do with the wind climate. The wind climate of the location belongs to the airport measurements or balloon measurements and aircraft measurements, etc. But these are primarily controlled by another team, not really structural engineers or wind engineers or architects. We don't have any control on those measurements. So these are primarily controlled by meteorological department. So in my opinion, we should be talking more to meteorological department in terms of what we expect from these measurements and etc. So there is a great disconnect there. So we can talk further in discussion. Now,
Suresh,
with respect, yeah, go ahead.
You again. For tall buildings or taller buildings, high-rise buildings, you're right. The loads are proportional to V cube virtually.
Yes.
And of course, that converts to cost, and I think that's the biggest challenge for us. It's the costs, and so your wind climate is very, very important. And I think that's something that that we have to emphasize to all the stakeholders, not just engineers and wind engineers. It's the cost implications.
Exactly. Cost implications are significant. And also, general belief is that I have to say that many people like higher numbers in terms of wind speed just to be safe. But I don't think, regardless of the number that you pick, you can never say that you are 100% proof. There is always an uncertainty. Uncertainty cannot be dealt with. Just keep on increasing the speed. That is not going to deal with uncertainty. Okay, we have to live with uncertainty, and there are ways to take care of that, and that is the way to go.
Yes, very good point.
So here, with respect to India, we can see primarily we have different systems, wind climatic conditions in India. For instance, synoptic winds of the order of 1,000 kilometers in size, which could be monsoons. As you know, right now it is passing through India, which is one of the systems which can produce not quite significant wind, relatively high winds at times. And then thunderstorms, 5 to 25 kilometers in size, can generate significant winds sometimes, but it is very, very localized. Sometimes, let us say a thunderstorm happening in Trivandrum, maybe the airport data is not picked up that thunderstorm. Maybe it is happening one side of the city, and the airport data may not record such thunderstorms. So that is one of the issues with the measurements of speeds in thunderstorms. Then cyclones. Cyclones are primarily coming and attacking our coastal lines. And this is also called typhoons in Japan and East Asia, and hurricanes in the North Atlantic Ocean. And essentially, these storms are the same, of the order of 500 kilometers or even more sometimes. It could be less also. And these storms, once it passes the land, it will die out, actually. It will die out and it will subside the intensity, because the intensity is all coming from the ocean. Once it passes the ocean, there is no energy. It is not feeding into the energy into the system. And then it will slowly dies off. And then it will become depression and deep depression and things like that, and attacking the interior part of India. And that's what we saw even in the recent cyclones. Once it passed the coastal line, it gets interior, and lots of downpour and rain-induced damages and things like that. So this is a short introduction. Now we have to get into how the international people are dealing with these things, because here are a couple of things we have to be very careful. One is basically the return period. Return period is the chance of occurrence of a storm on a particular year. For instance, if you say 50-year return period, means the chance of occurrence of that storm on a particular year is 1 by 50. That means you have 2% probability of that particular storm happening on any given year. So let us see how the Australian and New Zealand standard is doing. So basically here the question is, you have normal structures, you have post-disaster structures. Normal structure means typically all our high-rise buildings are normal structures. And post-disaster structure means, for instance, schools and hospital buildings, communication towers, very essential facilities or during cyclones, you can get people away from the coastal lines and make them as a shelter. I mean, schools and hospitals, not hospitals, schools are typically the shelters during cyclones. So how they deal with this, importance level 3 for normal structures. On 50-year design life, they go with 1,000-year return period. Here, we have to be very careful. A 1,000-year return period means it's an ultimate limit state design. And India is not in ultimate limit state design yet. We are still in 50-year working stress design right now. But how we'll go to 1,000-year design is we take the 50-year design multiplied by 1.5, which is our factor of safety to go into the 1,000-year design. And then for post-disaster structure, they have 50-year design life, they have 2,500-year design speed. So all they do is basically go from 1,000-year to 2,500-year return period speed to address going from normal buildings to post-disaster structures. You can see what is going on here. I don't want to go through everything, but they have regions similar to Indian code. We have regions too. We don't say ABCD, but they have ABCD region. C and D regions are the coastal regions of Australia. And those coastal regions are subjected to cyclones. And so they have very high speeds in those regions. Then you can see the top line is quoting the return period. You have 100, 500, 1,000, 2,500. So the 2,500 and 1,000, we already mentioned before, importance level 3 and 4. So going from 3 to 4, you are increasing the speed only about 4 to 7% or so. It is very minimal increase in speed, moving from normal structures to post-disaster structures. So this point, you keep it in mind, it's a very important point because what we are doing in our code, you'll be seeing so. So this is a major code. It's a very fantastic code, I would say, for wind engineering purposes, wind load calculations, and also they are following 3-second guess similar to our code. So AC716 is another fantastic code, even though nowadays it is getting bulkier, but it has lots of information in that code. And this is also following similar pattern like Australia. So the US has zones and they have return periods. They have 300, 700, 1,700 and 3,000 year return periods. And they are also into ultimate limit state design. So you have to remember that again, ultimate limit state design means very high return period. Now you see what is happening between normal structures to post-disaster structures. When you design normal structure, you go with 700-year return period. And post-disaster structure means you are getting into 1,700-year return period. So take the ratio of these two speeds. You're going to see 3/2 means you are having 6% increase in speed in the interior parts of USA. And then you have about 11% increase when you are in the coastal region. I took only Key West, Florida, which is one of the highest wind speed region. But if you go to New York, I don't think it is going to be 11%. It will be lower than 11%. So essentially, what is the summary out of these two slides is basically, when you go from normal structures to post-disaster structures, the increase in speed is, you can say, somewhere between 5 to 10%. As a consultant, I would put it in that way rather than going with fine numbers. Just 5 to 10% increase in speed. So when you have 5 to 10% increase in speed, you know the impact in loading wise. It is going to be increasing your load anywhere from 10% to 20% in cladding, and anywhere from 15% to 30% in structure already, okay? Keep this in mind, these are important information. Now I move on to slowly to the IS code, and then we can relate back to what we have seen just now. So IS code, this, I don't have to go through each and everything. Everybody by heart know that particular equation. Vz is equal to Vb into K1, K2, K3, K4. We are primarily interested in K1 and K4. And K1 was there even before. 1987 code has K1 too. So look at the K1, probability factor. It is written risk coefficient. We'll see soon what it is. And now the new introduction of the cyclonic factor, which is K4, which was not there before. And this is the point that we wanted to be discussing quite a lot in this presentation. Immediately, I'm moving to the K1 factor. So this is the K1 factor from the code. It was nice. I mean, we are designing it for 50-year return period. And then for important structures, that means post-disaster structures or important structures, which means hospitals, communication towers, power plant structures, and etc. The code is already saying that you can increase the speed between 5 to 8%. So remember what you have seen before. 5 to 8% looks very familiar because we have seen in Australian code, we have seen in American code, the same thing. So we are perfect here, I would say, because we have already addressed this from 1987 onwards, because this code is from 1987, which has been rewritten in 2015 or modified in 2015. That is when the K4 came into picture. Now you're going to see what the K4 is bringing. The K4 is saying that, okay, 60-kilometer wide on the eastern coast as well as on the Gujarat coast, where there is a suspicion that more cyclones are hitting that region and doing all of these damages. There is a perception that we have. The damages are caused by wind. Wind is termed as the villain, doing all the damages, okay? So what is the solution for that? Okay, come up with another factor. That factor is cyclonic factor. What does that factor do? Is it is supposed to be increasing by 30% increase in speed for post-cyclonic importance emergency shelters, which means hospitals, schools, communication towers, 30%. Okay, 30% means you have already increased 8% before with the K1 factor. Now you are coming with another 30%. So you know where this is all going to. And then industrial structures, that means cooling towers and chimneys, another 15% increase. But these things are too high, in my opinion. But another interesting thing you can see is the last line. All other structures is 1. All other structure 1 means if you have, let us say, we have done Chennai TCS Tower. TCS Tower is right at the coastline, and where people are working. So what it means, you have to use just 1. So are those structures not important? Why we have to, if you really think that the speed is increasing, why we have to leave that structure without applying these factors? You know, that doesn't look good to me actually, because if the structures, when the speed is increasing, it is equally important. All structures have to be, the same speed has to be applied to all structures, because otherwise it doesn't make any sense logically why we have to change. What it makes logical is right here, because for hospitals and communication towers and power plants, we say that, okay, these are important structures. So we have to design it instead of 50-year return period, go into 100-year return period, increase the speed by 5 to 8%, which makes logically perfect sense, and it also follows international standards.
Yeah. Suresh, that's very interesting. I just want to make a point in Australia. So effectively, we don't have a K4 factor, right?
Yes.
And the only thing in Australia for cyclonic, the only difference is that the wind speed in all directions is the highest wind speed. So there's no directionality. That's the only for cyclonic.
Yeah. Correct. There is no directionality. No directionality is 1. In C and D region in Australia, wind directionality is 1. I understand.
But the 30% wind speed increase, and then the forces increase by 60, 70%.
Yeah.
It's a big,
so,
big
and
effect.
Exactly. Then in addition to the K1 factor, this is going to be 2 times the load, you know, approximately 2 times the load. All right. So now we move on to certain points I want to raise. In addition to the K1 factor, cyclonic factor is raising the wind speeds to exceptionally high levels, leading to very unreasonable loads. And another point I want to raise is if these speeds really occur, no normal structure will exist, actually, because it is going beyond your factor safety. Typically in wind, you never might have seen any structural failure. Total structural failure you see in wind only for low-rise buildings and some shacks and things like that. You never see on a high-rise building, really a high-rise building is crashing down due to wind. You're not going to see that. I never seen that before. But you will see cladding failures and things like that, which is normal, okay? So that is why I'm saying if these speeds occur, then no normal structure will exist because it is going beyond your factor safety. Then another issue I want to raise it up here is cyclone-induced historical wind, extreme wind speeds are very rare. It is very rare actually, because you are relying on the meteorological station data. And when you look at the IMD data, sometimes we see that, okay, many hours and many months, there is no data. Then we ask the question why the data is not there. Then they say that, okay, high winds sometimes, we couldn't measure the data. We are not having the data. So that is why the land-based surface measurements and relying only on the land-based surface measurement is not a nice idea to produce cyclonic speeds. So let us see what others are doing. What others are doing in Australia and America is they are doing Monte Carlo simulation of cyclones, because we have lots and lots of information about cyclones. They understood everything about cyclone, how it forms, how many hours it will take, which path it is following, what is the translation speed, what is the rotational speed, all the statistics, everything is already built in to the system. Everything, all the history, everything is there. And we can utilize this and come up with Monte Carlo simulation. And you can simulate 100,000 simulations or 200,000 simulations and whatever you're looking for. And then you can predict properly the speed on any location. Now, since I brought up the cyclonic simulation, I'm moving on to the cyclonic simulation. Predictions, what is happening in important locations on the coastal line. I'm not going to be showing all the locations. Let us see Chennai and Calcutta. And these are the eastern coast. And you can see Chennai, you can see the blue dots, which is the mean hourly speed. And then you can also see the yellow or orangish line, which is the 3-second gust prediction versus the return period. And then I'm also plotting along with that the IS 875 3-second gust. These are the values at different return periods. So we are fond of looking at 50-year all the time because that is the one that we use in design most of the time. So let us look at what is happening at 50-year, which is right here, 50-year, the first dot. The code is predicting 50-year return period as 50 meter per second. And the simulation is saying it is only 40 meter per second. So this is based on 100,000 simulations of cyclones in the Bay of Bengal. And then you can also look at various other return periods, probably I think if you look at some of the higher return periods too, the wind speed predicted by the code is higher than what is in the simulations. Look at Calcutta, the same situation. If you go to the 50-year return period, it's about 44 meter per second. In comparison to 50 meter per second inside the code. So again, we are lower than what is in the code. So mind you that this is again, the cyclonic factor, bringing cyclonic factor here doesn't make any sense. You can basically think about that right now, because right now the wind speed map prediction itself is higher than the cyclonic predictions. So then do we really want to have another factor built into the code? And if you go to 1,000-year return period, you'll see it is kind of getting matched between the wind speed in the code, means using K1 factor, and then what is predicted out of the simulations.
Suresh, does that yellow line, sorry, the dots, does that include the 1.3 or no?
No, it doesn't involve downpoint.
Okay, so you amplify those speeds by another 1.3.
Yes, yes, yes.
So I just want to, so 70 meters per second is 240 kilometers an hour. And you multiply that by 1.3, you get to 300.
That is tornadic speed.
Yeah.
That is tornadic speed, you know.
Well, the world hasn't experienced it. The highest wind speed ever experienced in the world is, I think, 290 or 300 near Hong Kong.
Yes, yes, right. So these speeds are exceptionally high, and that is the reason of plotting all of these things, just to show you how, you know, it is comparable between the cyclonic simulation and what is in the code without the cyclonic factor. Okay, this is without cyclonic factor. That point is very important because I didn't code that right here in this slide. Now look at Mumbai. Of course, Mumbai, lots of high rises are coming, so everybody is looking at Mumbai and the recent cyclone. Just brushing through Mumbai. I think several other cyclones brushing through Mumbai before also. And because some of the cyclones landfall in Gujarat really passed through, outskirts of the cyclone passed through Mumbai as well. So look at the cyclone simulation, then again the yellow, you can see, because that is the 3-second gust simulation values, in comparison to the red dots, which is coming out of the code without cyclonic factor. So you can see what is going on in this location. For 50-year return period, the cyclonic simulation is giving 28 meters per second. And then the code speed is 44 meters per second. So you can see how different they are. Basically, the cyclones are, what this is saying is the cyclones are not quite important as far as Mumbai is concerned, because the cyclonic speeds are lower. But your thunderstorm wind events could be higher than the cyclonic events. Because if you look at just below, I have another plot which is from the airport data, CSI, Chhatrapati Shivaji International Airport data. And we are plotting with the blue line. And that line is giving me at 50-year return period. I didn't put a dot, but you can look at just below the green dot. That is about 35 meters per second. In comparison to the green dot, which is the IS 875, which is 44 meters per second. So this 35 meters per second includes cyclones, which includes thunderstorms, which includes monsoons, everything is included. In comparison to the 28 right here, which does not include thunderstorms or cyclones, any other types of storms. It's purely cyclonic storms. So I believe that the graph speaks by itself. I don't have to speak more than what the graph is saying, because it's very, very clear. Some of the doubts that we have, whether it is passing and etc. and etc. Look at what happened in the recent Nisarga, which didn't really pass through Mumbai. But we know what happened in Mumbai. The gust speed was around 60 kilometers per hour, less than 60 kilometers per hour, which means it's about 16 meters per second. 16 meters per second gust is return period wise, it is less than 1 year return period, less than 1 year return period wind. Okay, so because we are trying to relate, the perception is we are trying always to relate the damage with the wind speed. Some sheets are flying off, some failure happening, some trees are falling, some communication towers are falling. Suddenly we blame the wind. I think we have to step back and look at, okay, what exactly caused the failure? Did we really check the roots of the trees which has fallen? Maybe it is unhealthy already. So it will fall during severe windstorms. Did we prune the branches before the storm? Probably no. And you have to think other places, what is really causing these damages. You know, of course, you have to look at the wind speed also, but you have to come to an assessment like that, then only you'll come to know exactly what is really causing these damages. Now I slowly move on to the discussion. This is towards the last part of the presentation. It's a very interesting part of the presentation because I'm here bringing up numbers, bringing up the whole world actually in the picture. So before I bring up the whole world in the picture, let us look at our India and the Bay of Bengal Basin and the Arabian Sea Basin, what is going on. You can see all of these curves. Lots of cyclones are coming and passing at various intensities. The intensity you can't figure out from here because all of them are in black color, which you will come to know later, a little bit later. So what I wanted to tell you is that whatever is being formed closer to Burma or Port Blair region, where the vortices are being created in the ocean atmosphere, I mean, and the fueling is happening from the Bay of Bengal. Bay of Bengal is known for as a warm ocean. So lots of energy it is getting from the ocean, and then it is getting formed above Port Blair or nearby Port Blair, and then it is traveling. Why it is traveling towards India? Why it is not going elsewhere? The reason is because your upper atmospheric flow circulation in this particular latitude is between, our latitude is between 5 degree and 30 degree. And 5 degree and 30 degree latitude, the upper flow circulation is east-west. So whatever is formed in the air is being brought by the upper circulation slowly towards India. And that is the red arrow line is showing. So whatever is being formed, definitely it is coming and hitting India. Or it will get a turn also. Sometimes it will turn and go through Bangladesh or through Calcutta, for instance, in this particular situation. And that can happen because things are quite complex in the atmosphere. Twisting and turning is possible. And for instance, from 30 degrees to 60 degrees, wind is flowing from west to east, just the opposite. Okay, so in this particular latitude from east to west, in the other latitude it is go from west to east. So sometimes it will take a turn and hitting the other direction and etc. So now this will answer what is going on in Arabian Sea, because typically whatever is being formed, cyclones formed in Arabian Sea, near it is coming from Madagascar or nearby Indian Ocean. Then it is slowly moving and coming across the Arabian Sea and turning to the right and going and hitting Oman or Pakistan. The reason is upper atmospheric air circulation is from east to west. So it is taking this storm and going into the Oman region. And that is primarily the reason Mumbai is not getting hit with the many cyclones, because it cannot actually, it will go move away from Mumbai. Not only just Mumbai, I mean, even the southern peninsula is getting escaped, primarily because of these flow circulations. And Arabian Sea is typically not that warm as well in comparison to Bay of Bengal, but the reason incidences are saying that Arabian Sea is also getting warmed up because of the global warming situation, which I am not going to be discussing too much right here. Now, one important scale I wanted to bring up, Saffir-Simpson hurricane scale is kind of a, what can I say? I mean, any cyclones or any hurricanes or typhoons happens, immediately we'll compare with this scale. We always call Cat 1 hurricane, Cat 2 hurricane, Cat 3 hurricane. In that way, we know how important they are actually. So look at the 3-second gust wind speed over land, which it can bring. This is a very important numbers to remember. Then some of the damages it is quoting, which I'm not going to be discussing too much on these things here. For instance, look at India. We have 39 meter per second zone. We have 44 meter per second zone. Where are they in this plot? 39 and 44 comes into Cat 1. So we have Cat 1 hurricane or cyclone, if you want to call it. I mean, 39 in the eastern coast, sorry, western coast, even eastern coast down is 39. And then we have 44 in Mumbai, everything is Cat 1 hurricane. And then if you look at 50, 50 is Cat 2 hurricane. So that is the east coast is having 50 meter per second. So you can say that, okay, we have Cat 2 on the eastern coast and we have Cat 1 on the west coast. Okay, remember that this is another piece of information you want to compare when I show some other graphs. So look at the whole world. Now I'm showing the whole world. This is with colors, so you can easily identify the intensity. Fortunately, the southern hemisphere, maybe God is in favor here, I believe. The southern hemisphere is not getting major storms. You know, you can see there are a number of storms happening, but the intensity is not there with the southern hemisphere. But when you look at the northern hemisphere, you can see the actions where it is all going on. I mean, look at the Atlantic basin where Miami is. You can see several red dots and orange line. This is a very active basin. And look at what is happening to Africa on the right side. And you can see whatever is being formed in Africa is taken by the upper atmospheric circulation, because this is in 0 to 30 degree latitude. Wind is from east to west. So it moves to Americas, and it is hitting Americas because it is being brought by the upper atmospheric circulation. And what is going on in Taipei and Manila? I mean, that region is even worse, actually. Number of Cat 5s are happening there, number of them. Okay, Cat 5 typhoons, they call it typhoons, are happening there. And part of it is also getting passed through these gaps and getting into Hong Kong. Hong Kong is also pounded with some significant storms. You might be hearing the media. And then look at India. I mean, India is pretty soft, I would call, because it's a much pleasing colors here with blue lines, which is not too, catchy in comparison to the red. And that means you are getting much not very significant storms, not too frequent as well in comparison to what is going on in these locations. So I want all of you to remember this plot also for the next two slides, and then you'll immediately get where we stand in terms of the speed. So I'm comparing with the world, the east coast of India with the world. So you can see the latitude is written. Latitude, I'm comparing 13 to 23. Hong Kong is 22. Taipei, Taiwan is 25. Manila, Philippines is 15. Miami, USA is 25. So I have all the speeds written right there. You can see the values. 50 return period, 3-second gust speed at 10 meter height. India 50, and Hong Kong is 57.9. 60.8, 59.7 Manila, Miami is 58. So you can see all these are very close. Hong Kong, Taipei, Manila, Miami, look at these locations, right? These are kind of close. Now, according to Saffir-Simpson scale, where we stand, you can immediately compare on the side. In India, we are at Cat 2, 50 is Cat 2, you have the range right there. And these guys are all in Cat 3. They are all in Cat 3, even though you see the number of Cat 5s are happening. It is not just about one storm is passing at one location, immediately you bump up the speed. That is not very scientific. You have to look at what is the risk of occurring this stuff again and again. So you have to look at the probabilities, you have to work out the numbers. And that is the reason immediately they didn't go for Cat 5. Their 50-year return period speed is still in Cat 3 only. Okay, so these are Cat 3 speeds in comparison to our Cat 2 speed at the eastern coast.
And Suresh, on the west coast, it's probably even lower, right?
West coast is 39 meter per second, and we have 44 meter per second. That is Cat 1. Okay. That is Cat 1, which I am not quoting here. I went for a little bit significant storms in the eastern coast in comparison to the west coast. So here, the funny thing is, you can see the 65 meter per second I quoted just down. How I got that 65 is 50 multiplied by 1.3, because we have the magic 1.3 from the K4 factor. So when you multiply the 50 by 1.3, that is your 65. So where do this 65 stands? It is Cat 4. All right. So I think this is one of the reasons we need to look at what others are doing. They are doing a fantastic job with other international locations, and they are probably looking at speeds year by year and etc. So this is coming later on in my conclusions. So let us see how the ultimate speed, because eventually the structures are designed for ultimate speeds, regardless of whether you follow 1,000-year return period speed or 50-year speed. Because in 1,000-year speed, you follow 1,000-year speed with a factor safety of 1. And in 50-year return period, you multiply with 1.5 and you take that design loads to, you can say 500-year or 1,000-year or whatever the return period you want to say, because there probably we don't go there because it's all over the place in terms of return period. But we don't look at that. Let us look at plainly from engineering point of view. What is the ultimate speed in east coast of India? 61.2, which is Cat 3. How did I get this? I got 50-year return period speed multiplied by square root of 1.5, because I am multiplying for the load 1.5. So in speed, that is equivalent to square root of 1.5. So that is 61.2. And this 61.2 is coming in Cat 3 range. Look at where others are: Hong Kong, Taipei, Manila, Miami. They are all in Cat 4. Before they were in Cat 3. So in ultimate, in working stress, they were in Cat 3. In ultimate, they are in Cat 4. And we were in Cat 2 in working stress. And in ultimate, we are in Cat 3. So in layman's point of view, all of these make sense to me, at least, because I am watching climate, which is happening around the world. I am watching, regardless of the country, very closely on the climate aspects. So when I read all of these things together, at least at this point, I don't have any concerns in terms of, because the K1 factor will do the job without the influence or without the inclusion of the K4 factor. So with this, I'm concluding. Basically, I have some concluding remarks, and maybe after that, we'll take it up for discussion. So the question is wind a villain responsible for all wind-induced damages? These are perceptions basically in the media, because whenever I keep seeing this stuff happening all the time, because when the cyclone passed by or some storms happens, immediately I see some pictures, all failures, that this trees gone and power lines and low-rise buildings destroyed and sheets gone, etc., etc. And then they'll say, oh, high winds happen in that city, and this is the speed, some numbers are also there. But then I wonder, I keep reading those articles and see, okay, can I come to know where these measurements have been taken? Because as a wind engineer, I would like to know. I would like to know whether, did you make this measurement through satellite? Or did you measure it at 10-meter height or 100-meter height or 2,000-meter height? Because without that information, this speed is basically nothing to me, because it has no use for anybody without knowing certain aspects of measurements. And also another question, is it a gust? Is it a mean hourly speed? Is it a sustained speed for 1 minute, 2 minutes, 10 minutes? Without those information, again, I mean, I'm looking at Amphan wind speed. In Calcutta, they say 120 kilometers per hour happened. But till now, I don't know where it got measured. What is the averaging time? I don't know. So I really don't know exactly what really happened in Calcutta city. To me, at least that speed, I cannot translate into a speed which I can understand, or any structural engineers or any wind engineers can understand. High wind speed probably is not the reason for all wind-induced damages. This is the part that is getting interesting. Many times poor design and workmanship and maintenance is causing the issue. As you know, workmanship is a very serious issue. I mean, because even the building that I am living right now, some of the fantastic thing has been installed, put in place, but it is being installed by people who doesn't know how to install stuff. So then the whole purpose of those equipments are lost. So workmanship is extremely important, and then maintenance. Many buildings in India, there is the maintenance aspect is not taken care of. Once it is built, and afterwards, when the maintenance happens, if you have sufficient funding, then you will do the maintenance. Otherwise, it is left alone. So those are serious issues.
So, you mentioned poor design, and I almost like to suggest that all the damage is not because of poor design, it's probably due to no design. Most of the damage, and not just in India, around the world,
yes,
it's all got to do with non-designed engineers. Buildings that have not been designed. We're talking about houses, residential.
correct.
Would you comment there?
That is correct. Poor design, sometimes even the interpretation of the code itself is an issue. Because as you know, the codes are not storybooks sometimes. You have your own issue in interpreting from the code. And that could be another reason for poor design. And sometimes no design is also an interesting aspect, because sometimes, for 1-story, 2-story building, do you think that this is all going to get designed appropriately? Then the glasses are failing on a mall, a 2-story mall, and failure of glasses. I'm quite sure probably there is no design right there.
I just want to make a comment that, say, some of the developed countries where there are legal issues,
yes,
I'm telling you that during a cyclone, all the damage, you don't hear too many legal cases, because it's usually due to trees falling onto buildings or
yes,
roofs coming off and hitting things.
yes.
So I'm just saying that a lot of it's because of poor fixtures and fittings.
Exactly, yeah. Number of low-rise building roofs have been blown off. It is not properly. Sometimes, you have some kind of material on the roof, then you just put a sheet above that. So what do you expect during cyclones? It's going to fly, and then it is going to hit against another glass, and if that glass is broken, or that is going to hit against a communication line, then your power is gone, and things like that. So any loose elements in debris, that is called debris impact. So debris impact is a very serious issue during cyclones and during high winds, because all the loose material is going to fly off and then hitting against people and hitting against other structures. The next point is enforcement of code and interpretation of code. I just mentioned interpretation before. Enforcement of code is also very important, because I don't know whether sometimes there are loopholes with respect to the enforcement of code. As you know, that even in IS 875, when to do internal tests, it is written, but it is written in a very small font. In fact, in one occasion, I keep saying there is a limitation on the code, and this is in the code. Then the person is asking me where it is in the code. He could not find out. Then virtually I had to go and tell him the page number. I had to locate the stuff for him, actually, because it is written in a very small font and he couldn't find out. So I think the enforcement of code is also equally important, which, as you know, that recently the IS 16700 talking about beyond what heights we have to do internal tests, but we have to also enforce that, okay, below that height, we probably don't have to do internal tests, but we have to follow the code, actually. Because without following the code, if things are dislocated and damaged, whom we should be blaming? So that is something we need to be very careful on, the enforcement of code. This is my last slide. A few more conclusions. So based on our studies, actually it is not supporting the speed increase for the Indian coastal regions more than the current wind speed right in the code, which means I'm saying the K1 factor is sufficient, we probably don't need cyclonic factor, the code. And I did not talk about formulation of the cyclonic factor, which could be in the discussion, and that is also unsound in my opinion. And this is an opinion that I'm saying that it should be probably removed from the code. And we are sufficient we are solid with respect to the K1 factor. And then what I suggest is carry out detailed simulation studies and change the map if that's what we wanted to do. Because currently, even though currently there is no indication of speed, but we can still do lots of simulation because there are land-based simulations available. We can take upper atmospheric data from NASA, from satellite, and we can utilize the data to predict what is happening on the ground. We can come up with a better map for India, but for that you have to do some work. And we have done such work in the past, and the recent introduction of the GCC map in the Gulf nations is a product of our simulations for that particular region. Then finally, carry out wind speed studies continuously, because at least update the wind speed map for every, at least in 10 years, because that's what all the countries are doing. For instance, AC is doing this every 5 years, in fact, because you can see the Alabama region increased the speed from 105 to 115 mile an hour in a span of 10 years or so. So this exercise we have to follow. It is not that something, we find out and we come up with a code and just leave it. We have to continuously explore what is going on around us. With that, I conclude, and I think I'll leave the rest for discussion.
Suresh, that was fantastic. It really is fantastic, and I hope it stimulates an interesting Q&A session. But the main takeaway from all this that I get out of it is that it's not necessarily just lowering the wind speed, it's really getting the right wind speed, getting the correct wind climate. And what I see is that we really need to focus on the causes of the damages that occur when we do get cyclones, and don't blame it on the wind. We have to find out the cause of the damage.
Correct.
Because if we keep increasing the wind speed, we are counteracting another important factor in building design, that's sustainability. We are unnecessarily wasting a lot of materials with a false sense of safety. And we get influenced by damage and fatalities, and obviously there are political influences. Increasing the wind speed is not the right answer, but I'm hoping that we're going to stimulate some interesting Q&A following your presentation. Thank you very much for a stimulating presentation, as you always do, Suresh. Thank you very much. Much appreciated.
Thank you.
Suresh, do you want to make some concluding remark?
Well, I think what I can say is that we have to get into the details, basically get into the details of every aspect that we are seeing, because not just complaining about winds, but also we have to equally look at the winds also. We are responsible to look at the winds, parallelly look at how the damages are happening, and try to bring up, that's the only way. Sorry. Go ahead.
No, you go ahead.
No, that's the only way we can come to a consensus as to exactly hit the right area, rather than keep hitting the wrong area, and then we'll never reach to solving the problem.
Okay, thank you, Suresh. And like I said, I think all the stakeholders, including wind engineers, architects, structural engineers, the authorities, we have to work together to come up with the right solution. Okay, thank you.
Yeah, thanks a lot.